Okay, good. So, lesson 6. These are the objects we're going to talk about. Okay, these operators here. These are the basic operators of the theory, and they are derivatives on the group. So they generate, they turn these variables in the three directions of the algebra. And let me start listing some of the properties they have. First of all, by construction, Li, Lj don't commute if they pertain to the same link. So the three L here are like angular momentum operators. So epsilon, I, J, K, L, K, L, delta, L, L prime. So if they're on different links, of course they commute. But if they're on the same link, L, A, L, J do not commute. So we see a little bit of quantum mechanics non-commutativity here. Of course, they don't commute with this. These are derivative operators, so they act on derivatives here. Let's get to one of the main properties they have. When they act on states here, so on gauge invariant states, it's pretty obvious to see that the following equation holds. I'll just argue for it. So L vector, any component, so for each node, I have a node and I have four links coming out. Say L1, L2, L3, and L4, and let me just for simplicity imagine they're all oriented outside. So I have L1, I sum with L2, with L3, and with L4, acting on a gauge invariant state, so a state that satisfies this equation here, so a state here, I get 0. Let me write it more compactly. The sum over the links that come out of a node, I use this notation here, L psi is 0. This is called the closure equation, or closure constraint, or closure relation. Now, why it is true? Well, it's pretty obvious why it is true. What does this operator do? This operator acts on the HL. So let's suppose this is a node. This is the full H. So this operator acts on the HL here, act on the left, and it multiplies the left infinity. It changes infinitesimally this HL here, turning it in one direction of the algebra, and the second does the same here, and the third does the same here, and the fourth does the same here. Okay, so it's like multiplying all these four by a same group element, which is exactly what the gauge invariant does. So if you have a gauge transformation only on one node, this gauge transformation multiply the four group elements corresponding to the four links that come out from that node by gauge transformation. So in other words, this is the generator of gauge transformation on the nodes N.
So this is true for each I of the Li, for each component. This is true component-wise?
This is true for each I, for 1, 2, and 3. It's true component-wise. Okay?
What is the argument of this psi? Which
find the psi of HL, the HL sits on one of the links.
The
Which link is that on for this side? If there are multiple links.
this H is a function. This H is a function of all HL.
Of all links.
Of all of them. Is a function of all of them, and each HL here acts on one of them.
Okay.
Here, where only the four L's coming out of the same node.
Yeah.
So this is the infinitesimal transformation that act on the four group elements associated with these four links on the node, and that's exactly the gauge transformation there. That's a generator of those gauge transformation, and is zero. So this is if you want, it's like the Gauss law, right? It's a generator of gauge transformation acting on there. Sometimes it's called the Gauss law, or Gauss for the French. Good. So as I said, these operators here are defined on H tilde, not on H. So let's see what we can define on H. Well, we have to see, these are not gauge invariant, as I said. They're gauge variant because they have an index I. So when I act on a gauge transformation here, the L operators that sit here transform in the vector representation at the gauge transformation. So to write gauge invariant things, I have to get rid of this index dependence, and the simplest thing I can do is take the scalar product with itself for a fixed L, and this is an operator which is called AL square. So the actual operator called AL is the square root of that. This is a self-adjoint operator. These are all self-adjoint with respect to the scalar product of this Hilbert space here. So this is this individual knot is not, but this is well defined. Is well defined on the gauge invariant Hilbert space. It sends the gauge invariant Hilbert space into itself. That's one possibility. Another possibility is to do the same. Let's call it GLL prime. Is to multiply L with L prime, some of the indices for 2L and L prime that come out from the same node, and this is also gauge invariant. A third possibility, it's pretty obvious, is Li, Lj, Lk, epsilon I, J, K for 3 L's, not for the same L because of it will be 0 by antisymmetry, but for 3 L's, L, L1, L3, it's called V square, L1, L2, L3. And this actually depends only on the node, because it's pretty easy to see that if I, instead of L1, L2, L3, I put L1, L2, L4, I get the same object. Do you see why? It's because of this equation here. So if I have L1, L2, L4, I, J, K, epsilon I, J, K, L4, because of this equation, can be written as L1 plus L2 plus L3 up to the sign, but L1 and L2 gives 0 because of antisymmetry. So I can L4 and L3 give the same thing up to a sign. So up to a sign, and forget the sign for the moment, plus or minus this is uniquely determined by the node, and the sign just depends whether the parity of L1 of the three of the triple is positive or negative. So if I just put plus or minus for positive or negative parities of the triple, I get just one quantity. So these are all gauge invariant things. And there's a little theorem, which I'm not going to prove. In fact, yes, I'm going to prove, because I'm going to diagonalize these things, that the set AL Vn, okay, for all n and all n, it's a maximally commuting set of operators in the sense of Dirac. So it's like energy, total angular momentum, and Lz in the hydrogen atom theory, like L square Lz for the angular momentum. So in other words, you can diagonalize this together, and there is a basis that diagonalize this together, and there is no degeneracy in this basis. Right? If you states of a hydrogen atom, if you give the energy, the total angular momentum, and the third component of the angular momentum, you have a basis for the states of the electron around. This is the same, and in fact, I'm going to diagonalize these operators. I'm going to write explicitly this basis. I'm going to solve this spectral problem for these operators here, and this is going to be the spin network basis. And I'm going to do it probably not today, but probably this afternoon. But before going there, let me tell you what these things are geometrically, because that's where slowly the beauty of the thing starts to come out. And all this definition is sort of rigorous and precise, and I will solve the spectral value for this operator here. The geometrical interpretation is sort of sketching, hand waving, but it tells you what is going on. And we'll see a little bit more clearly in the classical limit, but I don't want to overplay it at this point. Let's get back to the geometrical picture in which we have our triangulation here. And so think this is a metric space, and there is a metric QAB of X, three-dimensional Riemannian metric, so this is curved, in general it's curved. And I'm going to approximate this matrix with the triangulation by assuming, as I said, that the tetrahedra themselves are flat, like the triangle on the heels, which are flat. So the curvature is when I go around, and in fact the curvature is on this segment here. Sometimes they're called bones. So this is flat. When I move to the next one, to the next one, to the next one, to the next one, I come back. I come rotated. There is curvature around these things here. So if I know the geometry of these objects, of each of the tetrahedron, if you know how big is each tetrahedron, the size of each tetrahedron, I know the geometry, because I just I can compute the angle here, and when I go around, the sum of all the angles, if it is 2 pi, there's no curvature here. If it's less than 2 pi, there's curvature. There's positive curvature. If it's more than 2 pi, there's negative curvature. So the geometry is coded in the geometry of the tetrahedra themselves. In particular, I can, if I know the geometry, I can compute the area associated to each triangle, and I can compute the volume associated to each tetrahedron. Well, it will turn out that this operator A associated to the link, remember that the link are dual to the triangles, is the operator corresponding to this area, and this operator V associated to this N is the operator corresponding to the volume. Let's do a little bit more, more in detail. When I will actually go back to classical general relativity and write the equations of general relativity explicitly, I will argue that it's much better to think of general relativity in terms of tetrad than in terms of metric, in 3-dimensional in terms of triad than in terms of metric, because this is much more general. You can do fermions. The old Einstein formulation in terms of metric is not good for fermions. In 3 dimensions, it means that instead of using QAB to describe the geometry, it's better to use the triad field, which has 2 indices, A 1, 2, 3, and I 1, 2, 3. This being a sort of general relativistic coordinate index, this being a internal flat index. The relation between these two is that QAB is E A I E B J just delta ij. So it's just the square. The triad is just the square. If you invert this equation, you can consider a quantity. This is a 3x3 matrix. Its inverse is written with A upstairs and I downstairs. This is the inverse of E A I. Is also called the tetrad field. Sometimes one is called tetrad and cotetrad. This tetrad, this cotetrad. I can write Q A B E A I E B J is delta I J, which you can think of this. This is a vector field. So this is 3 vector fields, E1, E2, E3. The index I is 1, 2, 3. This is a vector field. So a vector field in a point is a vector. And this equation says that you have 3 vectors such that E scalar product, EI scalar product with J is delta ij. This is a physical scalar product. So in other words, they are orthogonal and they have length 1. So instead of giving the geometry with a metric, you can give the geometry by giving in each point 3 orthogonal vectors, a reference frame. And if you know 3 orthogonal vector in every point, this is like knowing the metric, because from these objects you can invert them and use that and compute the metric. So that is the way of doing geometry, which is due to Weil and Cartan, which did it independently in different manners. Weil in more physicist way, Cartan in more mathematic way. Cartan called it a repère mobile. You have a repère in each point, and it's a way of fixing the metric. We call it triad in 3 dimensions. So we have this triad, and in any in the triangulated case, we can put a triad in each tetrahedron constant on the tetrahedron itself, and then a triad in another tetrahedron, a triad in another tetrahedron. So in other words, within each tetrahedron, we can choose a Cartesian frame and use it in this tetrahedron. When you go to the next one, you rotate it. And when you go around, the amount of rotation gives the curvature here. Now, if you have this tetrahedron and you have this quantity here, EIA, which is a function of x, you can do something with a triangle, which is the following. You can associate a vector to a triangle in the following way. Let me do it first using the language of forms, which is easier, and then do it in coordinates for those of you who are not familiar with form. This defines a one form, EI a dxa. So it's a form EI. It's a one form. Now, if you have a one form, you can buy a two form, EI EJ. This is antisymmetric in IJ, so you can put IJK and use a single index K here. And this is a two form, and two form can be integrated on surfaces. You can integrate on this triangle. So this gives a quantity EK. Actually, let me use JK I. So JK JKI, just to have the index I there. So to each triangle, you can associate a quantity EK, a vector, in some Cartesian three-dimensional space. The Cartesian three-dimensional space is the space of the triad itself. Are you familiar with this notation, or you want me to write it without using forms? Is everybody fine with that? Okay, everybody's fine with that. It's just, otherwise you just have to put coordinates on the triangle and write derivative coordinate with respect to derivative three-dimensional coordinate with respect to two-dimensional coordinate. You get the same expression. Now, what is this vector here? Well, think at it. Think this way. Suppose I choose Cartesian coordinate on the triangle, on the tetrahedron itself, such that EAI is just delta AI. I can, right? This is a flat metric. I can just choose coordinate, Cartesian coordinate, and choose a triad which is constant and is diagonal. The information is only when I go around bonds. So here, what do I get? I get an integration in Cartesian coordinates on the triangle of delta. So if the triangle is coordinate 1, 2, this is going to be 1, this is going to be 2, this is going to be 3. So this is only component in the third direction. So in other words, this vector here is going to be normal to the face. Okay? And in the integration, I'm going to give the area of the face. So this vector here is, if I call this normal, is equal to the area of the face times the normal. Which means that EI is the area square.
Just I think connotations. Shouldn't you choose either the wedge or the epsilon, but not both simultaneously?
No, the wedge is on the indices down here. Epsilon, ABC, the normal C. There are two different indices, and this is epsilon, JKI. So the epsilon is the upstairs indices, the wedge is the downstairs indices.
Can you say again what it corresponds to?
Sorry?
So which one is what is the correspondence between the indices and geometrically? Which one is the component? Which one number?
These ones are the general relativistic coordinates. This is the flat index in this in this basis. If you use, if I said that this is a flat metric, so if you use coordinates which are Cartesian, this becomes diagonal and everything is the same. Okay? But in general relativistic terms, AB corresponds to the general relativistic coordinate of the indices of the metric, QAB, these ones, while the IJK are the internal ones.
Now, maybe I've introduced confusion, but now you should.
What about the volume of the tetrahedron? Well, it's pretty obvious that if I know these 4 vectors here, I can compute the volume out of them. Actually, these 4 vectors have a property. There are 4 of these, right? 1 per each face. So let me call them E1. It's vector E2. E3 and E4. What happens if I sum them? Somebody has a guess? 0. And some of you know my preferred demonstration of that. It's actually a theorem by Gauss or something like that. But once I met Roger Penrose, and I was telling him about that, and I said, well, they sum to 0. And he said, how do they sum to 0? Well, how do I prove it? And I said, oh, yes, I have a proof. And Roger Penrose's proof was the following. Take a tetrahedron, solid, not just, okay, put it in water, and squeeze the water with a pump. What happened? Nothing. Okay, it doesn't move up and down. But when you squeeze it, there is a force, and the force is normal to the face, and since the pressure is constant, it's proportional to the area. So the force is given by this vector here, and since when you pressure it doesn't move, the sum of the forces must be 0. So that was Roger Penrose's proof that the sum of the 4 vector normal to the faces and proportional to the area is 0.
It's also called the théorème de la cocotte minute.
Théorème de la
Cocotte minute.
Uh-huh.
You know, it's this stencils in the kitchen.
Cocotte minute, la pentola a pressione in Italian, I don't know in English.
Cook with the steam. So théorème de la cocotte minute, and of course it can be generalized to any polyhedra.
Yes, that's right, and it's always true for any polyhedra. It's very easy to prove. In fact, if you write in coordinates, it uses one of these variant of Stokes' theorem ideas. It's just quite immediate. So they satisfy this equation here. And what about the volume of the tetrahedron? Well, the volume must be something you can compute in terms of all four of these, or 3 of these, given that one is, and should be a scalar. So there's only one thing that it could be, and should be invariant under the volume. It does not change if you rotate it. So you must construct a scalar out of 3 of vectors, which is invariant under rotation. There's only one possibility. So the volume should be some number, which we can figure out easily, and then epsilon I j k, e I, e j, e k for 1, 2, 3, for 3 of these. And the number, let's see if we can work out the number. Do it here.
The vector EI, I mean, the I is an internal index. So why are we saying that is the vector normal to the surface? I mean, I would imagine vector normal to the surface to be EA or not EI. it's because of the age.
That's right. That's right. So if you write this in this gauge, this becomes the. That's right.
And in general, would be something.
In general, they are not connected. It doesn't mean anything. You have.
That since we have the gauge invariants there, we can always choose. I mean, whatever triad you choose inside.
No.
We give the same.
Yes, you have a triad here, and if you turn the triad, if you think geometric, if you turn the triad with respect to the turn of triad, the vector turns, but not with respect to the tetrahedron itself. So that vectors does point in that direction with respect to the tetrahedron.
Sure.
It's just that the way you write in terms of the triad depends on the orientation of the triad. Now, just to make things a little bit concrete, let's compute this number here. It's very easy. This has to be the same for every tetrahedron, so let's not use a regular tetrahedron like this one. Let's use a tetrahedron which is this is length 1 in the x direction, this is length 1 in the y direction, in the z direction, in a Cartesian coordinate. So so then the areas are all 1 times 1 times 1/2, and the volume is 1/3. I forgot. 1/3 1 cube, so 1/3. So I need a square here, dimensionally. So v square is 1/3 square. A square is 1/2 square. So if I use this one, epsilon jk, they point in orthogonal direction, so all the angles are pi half, all the cosine are 1. So this is this number in that particular case times a times a cube. Yes, v square is the same dimension of a cube, but a cube is 1/2 to the 6, and v square is 1/3 square. So I get the coefficient here, which is so the number here is 3 square over 2 to the 6. I hope I've done it right. You see the logic. So you can get the number here. So the volume is proportional to that. That's not very important. It's just to make this a little bit more concrete. So you see, I can describe the geometry of a tetrahedron with 4 vectors, one per each face, with that satisfy this condition here, and the area is given by that, and the volume is given by that. Well, it does resemble enormously what the operators that we have constructed here, right? And in fact, the operators L, this operator L here, associated to links. Remember, the links are dual to triangles. These are exactly the quantization of this quantity here. And this actually can come out from a canonical quantization of the theory rather cleanly, because if you write the action, and you have the connection, the conjugate momentum of the connection turn out to be precisely this quantity here. Or more precisely, since the action, remember that the action is one of general relativity is one of 16 pi g something, there is a g here. So the conjugate momentum of the connection is going to be this quantity here divided by g. Okay, so the operator corresponding to the momentum is going to be this divided by g. So this thing here is going to be g times the operator. The operator is going to be a derivative, so it's going to be gh bar times of a derivative. So the relation between this and this is going to be that this is going to be gh bar times L. So this associated to a triangle is going to be this operator here multiplied by gh bar of the link dual to that triangle with a number here, 16 pi something, which we'll figure it out when we do things precisely with the action, when we write the action precisely. So we'll figure it out, this number. So out of this number, this geometrical operator here, the geometrical quantity here, in the quantum theory, becomes the operator gh bar left invariant vector field. Let's see if it works dimensionally. Here we did math, everything was dimensionless. Okay? gh bar is a length square. Is a Planck length square in C equal 1. And this is a length square, is an area. In fact, I said E is a normal vector with a length proportion to the area. So it matches, the dimensions are correct. Okay? So this thing which I've defined are going to have an interpretation as once multiplied by gh bar as the operator corresponding to this vector normal to the face of the triangle corresponding to the dual of this link and with a length proportional to the area, which means that its square is the area square, and this triple product of 3 is the volume of the tetrahedron. Okay? Are you with me? So now we have a Hilbert space, a set of operators, and some operators to which we definitely are going to associate the geometrical interpretation. Yes, Pierre?
So you were saying that the areas and the volumes formed maximally convoluting sets. I was wondering if one could imagine an operator for the combinatorial aspects of the graph.
No, the combinatorial aspect is written in the algebra, in the structure of the algebra itself, because these are attached to links and have this property here. If you want, the Hilbert space knows who is next to whom.
But just looking at the algebra of the operators, it's possible to reconstruct the...
Yes, just looking at the gauge invariant algebra, it's possible. Not at the gauge variant, but the gauge invariant algebra of operators knows about the structure of the graph. In a non-obvious way, but in fact we work the other way around. We fix the structure and then we build the algebra out of that. I wouldn't know how to do it explicitly, but the algebra itself knows about The gauge invariant algebra knows about the structure of the graph. Yes?
Are these results like independent of the triangulation? Like if you try to triangulate this with cubes instead of tetrahedra, then you would have 6 independent vectors in that case. Would you then have 6 independent operators, or is it
there is a lot of work for doing things not with tetrahedra, with this polyhedra, which has been done also here in Marseille quite a lot. Most things go through, but not all. So I don't want to go into the details. So you can still have this n, you can still write the volume in terms of that, etc., etc., etc. There are some things which become more awkward to do that. So it's much easier. Yeah. Yeah.
So this big E's correspond to the big L's. What about the small E's? Could they correspond to some operator?
No. Between this and this, it's essentially they're the inverse. Even if written in this way, it seems. So the relation between the two. First of all, these are the continuous variable. These are the integrated variable. But let me erase that. I don't need it anymore. In fact, that it was born. If I have EAI, its inverse EIA. Let's write the formula of the inverse explicitly. Is the determinant of E epsilon A B C epsilon I J K E I E J B C, right? That's how you invert a 3x3 matrix. The standard formula of inversion of 3x3 matrix. So you see that this quantity here, I put the determinant here. This quantity here, it's exactly the inverse multiplied by the determinant. In fact, historically, that's how it was born. It was born as when Ashtekar did the Ashtekar variables, the conjugate variable to the connection turned out to be not the triad, but the inverse triad multiplied by the determinant. And then this is actually a two form naturally. Maybe I should do it the other way around. So the determinant of EAI is epsilon ABC, epsilon IJK, EBBCJK. So that is the Ashtekar variable EAI. That's how it's defined. It's the inverse triad multiplied by its determinant. That's actually the conjugate variable to the connection. That's why it becomes a momentum operator in in the theory. And this is a one form, but this epsilon ABC one form is a two form. So the Ashtekar variable is actually a two form geometrically. Since it's a two form, you can integrate it over triangles naturally. And so this is the operator L. In fact, the way it was born is via the Ashtekar variable, and then this quantity here, and then this being a two form geometrically is naturally integrated on surfaces, and that is the operator we're talking about. So, of course, you can now go back from this definite inverse, but it's going to be a complicated operator. This is a natural operator in the theory. Good. So I have given you a sketch of an interpretation. Now we're going to actually solve the spectral problem for this operator. So we find the eigenvalues and eigenvectors explicitly. Or if you want the harmonic analysis, using the harmonic analysis of the group. And this will be the eigenvalues of area and volume of the geometry. So this gives with the discreteness of the geometry. And this would be next lesson. Good. Food. Can somebody push a button on the... Thank you.